Welcome to Radiology Reimagined at RSNA 2025. My name is Uzair Javaid, and I'm a second-year radiology resident from Texas, and it's a pleasure to be here. This first AI-driven clinical scenario is called AI-driven hydrocephalus detection and monitoring, and please note that this demo is running live, and everything you are seeing is flowing in real time. For the purposes of this demo, the images may not line up perfectly, but because they are actually taken from different patients. The demonstration is about 15 minutes long. So let's set the clinical stage for our first scenario. Frank is a 65-year-old male who presents to the emergency department following a fall. He's found to have headache and altered mental status. The ER physician quickly determines that Frank needs a STAT non-contrast head CT. The CT is acquired and the images are sent to our PACS, in this case the Visage 7 Enterprise Imaging Platform via Newton's Tree, our enterprise AI orchestration and end-to-end governance program. Newton's Tree sends the right study to the right AI product at the right time to analyze the images and send the results to PACS, RIS, and EHR systems for further visualization, processing, and storage. Unfortunately, the initial head CT discovers regions of intracranial hemorrhage, including subarachnoid and subdural bleeds. At the same time, our study is also forwarded to Icometrix. Specifically, an Icometrix product, IcoBrain, one of the leading AI-based quantification software for brain MR and brain CT. Here we demonstrate the capability of detecting and monitoring hydrocephalus. Brain CT scans are volumetrically assessed and compared with normative data, allowing to detect abnormal patterns of intracranial pressure. By following the patient over time, subtle but very clinically relevant and sometimes catastrophic changes can be detected and acted upon. Because of the intracranial hemorrhage, Frank is admitted to the hospital and neurosurgery is consulted. No acute surgical intervention is recommended. However, follow-up head CTs are ordered for overnight to ensure stability of the findings. So at 2 a.m., Frank is brought to imaging again for his repeat head CT. The scan is pushed to Newton's Tree and directed to both the Visage 7 PACS for storage and visualization, and Icometrix to quantify any variations in the intracranial pressure, as you can see on the right monitor. While it looks like the hemorrhage has not significantly changed, Icometrix detects that the ventricular size may be increasing. Icometrix automatically analyzes Frank's ventricular size and volumetric changes between the current study and the baseline. It then generates a structured report that includes a ventricular volume, interval percentage growth, and a trend chart. Newton's Tree receives these results, and if the ventricular volume changes higher than the defined clinical threshold, alerts Epic to prioritize this case. Epic now brings the study to the top of the radiologist work list. We're now in the Epic patient summary window. Here we can see an AI-generated comprehensive medical history and current symptoms. There's a generative AI solution that works behind the scenes to extract relevant info from our patient's charts via the EMR, and we see that this patient summary interface displays our patient's presenting symptoms as well as his current workup. The radiologist reviews these findings, confirms them, and hits the sign button in reporting to exit the workflow. Done. The ordering doctor logs into their computer before rounds and notices an alert in their inbox. The message contains an update that Frank's CT report was finalized and a link that takes them to the patient's chart, where they see our practice advisory. Upon opening the chart, Frank's doctor triggers the CDS hooks workflow and a CDS card is returned. Briefly, an aside about CDS. CDS hooks are an HL7 specification for clinical decision support to integrate CDS clients like EMRs. Hooks, like opening the patient's chart in the EMR, trigger a CDS call, which triggers a feedback. Information or suggestions are returned to the clinical user based on the triggering event. These CDS hooks can help us bridge our imaging reports and the EMR. The Epic integration demonstration demonstrates the values of CDS hooks to communicate actionable information from the radiology report to the ordering provider. Thanks to CDS hooks, Frank got a ventricular catheter before further clinical deterioration relating to his hydrocephalus. So before we close our work list, our next patient, John, presents the ED after experiencing acute vision changes. John is known to have multiple sclerosis, and after excluding an acute stroke, an MRI is obtained. Coordinating the patient's care requires tight integrations between systems like PACS, EMR, reporting, etc. Many people probably don't know that these systems speak standards like DICOM, HL7, and FHIR, and don't realize the essential role a product like the Qvera interface engine plays behind the scenes to enable said integrations, which is a key component of interoperability. The Qvera interface engine acts as a translator of these standards between systems to ensure that all systems can communicate effectively and just makes everything work. The MRI is acquired and the images are sent to Newton's Tree, our enterprise AI orchestration and end-to-end governance platform. Newton's Tree processes the study and sends the images to Siemens AI RAD companion algorithm to be analyzed. The Siemens AI RAD companion Brain MR AI product has two applications. Number one, brain volumetry and morphometry, which is essentially a segmentation of brain structures and volume computation, which is compared to an age-matched normative range. And number two, white matter hyperintensity lesions, which can be detected, segmented, counted, and calculation of the volume of white matter hyperintensities. So these results are visualized in the Newton's Tree AI review console, where the clinician can verify that John has multiple white matter lesions, some of which are new compared to the most recent prior exam. Once the clinician approves, Newton's Tree sends the AI results to Visage for further visualization and storage. So that was a lot of information. Let's think about how we will actually dictate this in our report, because it is a lot of information to report. Counting and comparing lesions is a very tedious job that I can personally vouch is not a very fun thing for a radiologist to do. But here the values are automatically sent to RAD AI reporting, which then populates the appropriate fields in the report and generates a personalized impression based on your own reporting style. RAD AI is one of the leading provider of AI-powered reporting automation, supporting thousands of radiologists daily with dictation and impression workflows that save up to 25% of time per report. Because the AI results are coded in the RADLEX lexicon and other coding systems, the AI results are easily and automatically populated into the report template. Please note that our demo shows an abbreviated version of the report, and again, none of these measurements were actually manually entered by the radiologist. So how do we monitor these systems to see that they are actually working adequately? So over time, we want to look for any decline in performance or drift by comparing our local performance with that of a nationally established benchmark, which is where ACR's Recognized Center for Healthcare AI comes in. This designation of ACR's Assess AI is the first national registry for real-world monitoring of AI algorithms for medical imaging. It provides longitudinal concordance data between the algorithm results and the radiology report, allowing for robust performance surveillance. Here we see the national dashboard on the second monitor showing the geographic makeup of the registry, the use cases we are monitoring, as well as the incidence of those use cases nationally. We can filter by case characteristics, such as patient demographics and scanner manufacturer, to give us an idea of how our site's unique practice environment fits into the registry. So now we'll see the second dashboard. It shows us concordance rates between radiology reports and the AI results for a specific AI vendor and model over time. This lets us visualize potential model drift or changes in the use of tools, allowing us to pinpoint a specific time to analyze factors which may have contributed to a drift of the model. Here we see data reported for the entire year with the box and whisker plot representing the distribution of concordance rates across the nation, and the stars representing specific facilities, allowing a comparison of how AI concordance rates at different sites will compare with a national benchmark. And it appears that one of these concordance rates at one site is much lower than the others, suggesting that it may be time to analyze our data to determine the root cause. So in this third and final dashboard, we can drill down on specific factors related to modalities, manufacturers, demographics, and other factors that could be contributing to drift. Here we can see individual records and better understand trends that may warrant an intervention. We can review individual cases in the Assess AI Forensics app, which can be used to provide feedback on the radiology report, AI results, and the images. So that was a lot of information, and that brings us to the end of our demonstration. Just to sum things up, we hope that you consider the following takeaways. The architecture of the overall system for the hospital is critical for seamless communication between systems. Number two, requiring international standards such as DICOM, HL7 FHIR, and the IHE profiles will enable interoperability. Number three, required structured coded semantic systems such as RADLEX, LOINC, and SNOMED will make the AI and other data interoperable throughout the system. And number four, you must ask for the use of these standards in every RFP for every system. Additionally, some of the other aspects of this demonstration show how AI can improve the workflow both on the interpretation side as well as the image acquisition and storage side, improving the radiologist workflow. Thank you so much for your attention. I'd like to emphasize one last time that this demo was live and the result of months of preparation by our vendor partners. Please give them a round of applause, and thank you so much.